Hi everyone. Uh, this is the demo video for Sentinel project. Uh, so Sentinel is a thermal aware self-healing AI ops load balancer built for distributed AI inference workloads. So the motivation behind the project came from a simple observation. Most load balancers react after a node becomes unhealthy. They wait until latency increases significantly, health checks fail, or the node becomes overloaded. For AI inference workloads, especially GPU and edge deployments, failures often follow a predictable pattern. Temperature rising, latency increasing, error rates begin climbing. Eventually, the node throttles or fails. The question I wanted to explore was, can we detect those warnings, sign early, and proactively shift the traffic before users experience degraded performance? So that's exactly what Sentinel does. The platform combines thermal aware routing, dynamic load balancing, circuit breakers, cooling off periods, automatic job rerouting, chaos engineering, self-healing recovery, real-time observability. So let's take a look. Uh, Before we start, I want to clarify something. Uh, Sentinel is just not a dashboard simulator. The metrics you are seeing here are not hard-coded front-end or front-end animation. When I launch the platform, Docker starts multiple independent services. These include one fast API orchestrator, four worker nodes, individual monitoring services, the React dashboard. Each worker node is a separate running service with its own state and API endpoints. The orchestrator communicates with those workers over HTTP and continuously poll them every 3 seconds. When I trigger a chaos event, such as a temperature spike, CPU overload, packet loss, or node failure, I am not triggering a front-end animation. Instead, an actual API request is sent to the worker. The worker changes its internal state, and the orchestrator detects the change through health polling. Routing decisions are then recalculated, traffic distribution changes, logs are written into SQLite, and the dashboard reflects those changes in real time. Similarly, inference jobs are routed to actual worker service. Uh, if a worker becomes unavailable, requests are rerouted automatically through the failover mechanism. The dashboard is not the system itself, it's the visualization layer on top of the cluster of independently running services. With the clarified, with that clarified, let's start the platform. So I ran this Docker compose up my spirit command. As you can see, Docker is starting multiple containers. Uh, we have the orchestrated, the four worker nodes, and the dashboard. Yeah. So all the worker nodes are currently online and running smoothly. So before we start testing failures, let's quickly walk through the dashboard. At the top, we have cluster-wide statistics. These include number of online nodes, average CPU utilization, open circuits, nodes currently cooling off, and the nodes that are in chaos. And here we have the chaos lab, in which different methods to increase the temperature or the CPU usage can be done, or we can drop packet, or we can spike the latency or kill the node forcefully. So here we have the node cards, different node cards, which tells us the different information about that node. You can see here the current status, CPU utilization, memory utilization, die temperature, routing weight, and P99 inference latency. Each card also contains live charts showing metric trends over time. You can change from here the duration of how much data you want to see. So yeah, it will show the past saved data also. So yeah, so now at the bottom of the dashboard we have the logs. These logs capture routing decisions, inference delivery activity, and self-healing events. Now let's generate some traffic. I will click on start traffic and you will see how the CPU utilization will go up and the routing weight decrease as we gave the jobs to particular nodes. Now I think all the nodes got some jobs. That's why the routing weight decreased. You can see here. Yeah. So this creates a steady stream of inference requests flowing through the cluster. Notice that all the four nodes are still healthy and receiving traffic. And uh, this is our baseline operating system state. Now let's see how the platform behaves under the failure conditions. One of the most unique feature of the Sentinel is thermal aware routing. I'll select node 1 and then click on spike latency, spike temperature. First, let me stop the traffic to see the difference in uh, CPU utilization, the different nodes, because right now all are getting jobs. That's why you will not be able to able to see the difference. But yeah, now the CPU temperature and RAM are going down of different nodes. And of node 1, you can see CPU and RAM going down except of temperature. Temperature still is going on plus 75, and right now cooling off is running. So after some time, automatically the temperature will drop, and yeah, you can see here the temperature automatically drop, and now this node is also working fine without any crash. And uh, traffic, because the traffic shift toward the healthier nodes, and you can see here self-healing event appear in the logs. Yeah, different messages regarding node 1 was shown here in every 3 seconds, right? So it's still online. Traditional load balancers would continue sending traffic, and also the Sentinels proactively reduces traffic before performance degradation becomes visible. This is the core idea behind the project. Now let's overhead another node, node 4. So I'll click on the overload CPU, and you can see here the routing weight decreased. Once it crosses the configured threshold of 85%, the circuit breaker will activate, right? And the node is temporarily removed from the routing decisions. Notice it that no new jobs will now be given to node 4 when I will start the traffic. Uh, Node 1 is getting, you can see here. And here also after some time this node will stabilize and all the CPU, RAM and temperature will go back to its normal state below 75%. And yeah, here you can see node 1, 2 and 3 are getting all the jobs. Node 4 is not getting any job. So traffic is automatically distributed across healthier nodes. This prevents the overloaded nodes from affecting the rest of the cluster. Now let's simulate the complete failure node. I'll select node 3 and kill it. Right now I'll stop the traffic, and you can see this node is also uh, yeah, I'll kill node 3 now uh, forcefully. So this node has become offline. So this is the easiest way to verify that the system is real. I'm not hiding a card from the dashboard. I'm stopping communication with an actual worker service. The orchestrator detects the failure through the health pooling. The nodes is marked unavailable. Any jobs that would have gone to that worker are automatically rerouted. If you watch the logs, you'll see rerouting events being recorded. And also, even though the worker has failed, the cluster continues servicing requests here. If I start the traffic, right, you can see the CPU overload that I did has now become like stabilized, and now after starting the traffic, it will go again up, and you can see here the node uh, reran itself after being stabilized, right? So this demonstrates the automatic failover and job rerouting, and also the restabilization and restarting of the node. So the built-in chaos engineering lab supports also the spike latency, drop packets, and and the three that I showed you. The goal is to validate system resilience under realistic failure conditions. Instead of guessing how the system behaves during failures, we can now observe it directly. Now let's recover the cluster. Like I want to show you the recover all function. I'll overload the node 3 and node 1. I'll simply kill every node. Yeah. So now I'll click recover all, and you can see all the nodes came back. Yeah. So the recovery process clears the chaos state, resets routing weights, closes open circuit breakers, forces immediate health checks. Within a few moments, all the nodes return to the healthy state. Traffic is balanced again. The entire recovery process is recorded in the self-healing logs. At this point, the cluster is back to its original healthy state. Also, other than this, we have this uh, the dashboard. We have fast API automatically generating interactive documentation. You can see here. Some key endpoints include get cluster health, get routing logs, get healing logs, post submit inference job, post trigger chaos experiment, post recover nodes, etc. Let's execute a cluster health request. Try it out, execute, and now you can see the different nodes status. You can see here CPU, RAM, temperature, etc. Information about the different nodes, and this makes the platform easy to integrate with the external automation system. So to summarize, Sentinel, it is a thermal aware self-healing load balancer designed for distributed AI interface workloads. The platform combines dynamic load balancing, thermal aware routing, circuit breakers, cooling off periods, automatic job rerouting, chaos engineering, self-healing recovery, and real-time observability. The central idea behind the project is simple. Instead of reacting to failures, predict them early and shift the traffic before the user are affected. So thank you for checking out Sentinel. Feel free to explore the code base, architecture documentation, deployment guides, and experiment with the chaos engineering lab yourself. Thank you.